and start chapter 2, the quantum mechanical model of the atom. Now with chapter 2, what's really important for us is just to bring about what the heck were people thinking. Now, what's amazing about this chapter and why it's one of my favorites is that it gives us, again, the history, the background. Where did we come from? Some of the big name players in the development of quantum mechanics. Now, this is really taking the atomic model straight to where we are today. The atomic model explains the strange behavior of electrons. It wasn't until the early 20th century that scientists began to investigate the quantum realm, the subatomic realm. Now, 20th century, this is around 1910 to 1920. 100 years ago, we still did not know what the heck was going on with the subatomic realm. And it was not until this time, until scientists started to investigate and seeing different results depending on what lab you were in. And that's where these main scientists, Albert Einstein, Niels Bohr, de Broglie, Max Planck, Heisenberg, Dirac, and Schrödinger, and some others, but these are the main players, started to really investigate together this quantum realm, this really, really small, what about these electrons? And why are people getting weird results depending on their experiment setup? Who's wrong? Who's right? And so their investigation really laid the foundation of our current understanding of matter. A lot of these scientists really hated quantum mechanics at the end of the day. It is very complex. It is very, very pull your hair out. I don't understand it, but it works. For everything that we can think about, these scientists really brought us into this new realm of understanding how electrons behave. Not that long ago either. And so what all of these scientists pretty much did is develop the idea that electrons are small, but the atom depends on the electrons. So even though we look a lot at mass and we do a lot of mass conversions in the lab and we're looking at the protons and the neutrons solely for that, we don't want to forget about the electrons. And they were pretty much overlooked up until the early 1900s. Just a little bit of background in this. If you've ever heard of the Schrödinger cat theory, let's just explain what that was. Schrödinger developed this theoretical paper. He wrote it. It was a paper published early 1900s. However, it was a theoretical paper. He did not actually do this, but he was trying to explain exactly what quantum mechanics was trying to explain, but for the everyday scientist. Now, not the everyday person, the everyday scientist. So still somebody that was understanding of chemical behavior, but that's how complex this actually is. He took a cat, theoretically. This is why my family told me, don't go be an artist, go be a chemist. Here's my cat. Nice. And he put him in a box, theoretically, right? Now, also in there, he put a vial of hydrocyanide, which is poison. Sad day. He sealed it though. He was a good chemist. He sealed it with a radioactive isotope that was set to decay and release the poison to the cat. Super awesome. He sealed this box all up and he said, this is an electron. Now, if you think that this is crazy, yeah, he might have been a little nuts because of quantum mechanics. But think about it. He said that before observation, so before he opens the box, right? Opening the box to see if the cat is is still there, alive or dead. He said, before I open this box, I've sealed it all up. I've put the poison in there. I put the cat in there. I've sealed it all up and I shoved it to the side. And I'm waiting. Before I open it up, I don't know if the cat is alive or dead. But the cat can be thought of as both. Because when I observe, I force the cat into one state or the other. By observing, by opening the box, that is me forcing the cat to be either alive or dead. So there's this duality before opening the box that we don't know the answer, but it could be either. It could be both. We don't know. And what he was trying to simplify is this idea that electrons are like in a box. Before we experiment, before we observe, we don't know what that electron is doing. And there's an actual duality to its nature. Electrons have a duality just like the cat did. Their duality is called wave-particle duality. So the cat had the duality of being both alive or dead. And by opening the box, we forced it to be either alive or dead. It can't be both when we observe it. And the same thing goes for the electrons. The electrons have this wave-particle duality, this nature that is so difficult to understand. We try to observe it. But when we do, we force it to either act like waves or to act like a particle. And that's the problem with experimentation. We don't know how to observe both of these at the same time. And so with Schrodinger's cat, what we have to be able to think about is when we look at all of the experiments that are in this chapter 2 information, we will be looking at electrons in one of two ways, either as a wave or as a particle. But it's really the merging of those two ideas that gives us the holistic picture of how electrons behave. And so that's what I challenge you to do. When we think about the quantum realm, we gotta think that any time we are faced with an experiment, what are we actually looking at? The wave nature or the particle nature? So here's an example. Yes, they discovered that there is absolutely small matter, extremely small pieces of matter, such as the electron, that behave much differently than a large macroscopic realm, right? The electron does not behave the same way as a desk does, but a desk is composed of millions and millions of electrons. So where's the difference? The absolutely small matter does behave differently because it's in a different world, right? They exist in two conditions. They either have wave nature or they have particle or matter nature. When we get into the macroscopic world, it's very difficult to see the wave nature. We see a lot of the particle or the matter nature. So an electron does have mass, right? And it does have volume. That's particulate, that's matter, right? And we can measure the mass. But under a different set of experimental conditions, it might have energy-like characteristics. This idea of bringing together wave-particle duality was a huge concept in the early 1900s. Back then, scientists did not know that matter could be the same thing as energy. They thought they were two separate things. Matter was matter, it had shape, it had mass, and energy, heat, or any other sort of energy was only contained in this other realm of energy. that had no mass whatsoever. But the electron is an interesting bridge between those two things. So what does it tell us about electrons specifically? It helps us explain that electrons exist and they behave in atoms in one of two ways. They can look like light energy, right? And they can express and they can absorb energy or release energy in the form of light. We will investigate that in spectroscopy next time. And we do know that they have mass and there is a position within the atomic structure, right? We talk about the electrons are just swarming around in that outer area. They take up most of the volume, right? And they're not a huge bit of the mass, but they're still physically there, right? So we're going to try to investigate both of these natures. The light nature is the one that is probably new to most people. Quantum mechanics is the foundation of chemistry. It explains our periodic table, which was developed before quantum mechanics. The periodic table was 150 years ago. Quantum mechanics was only 100. So the periodic table was set up, and now we can explain why it works the way it does. It's beautiful. We can also explain the behavior of elements in chemical bonding. That's something that we'll get into a little bit this semester, a lot in Chem 150, and even more in organic chemistry if you have the joy of continuing. And it also expresses the colors of their atoms. How cool is that? Fireworks. Why are some elements used in fireworks? It's because of the electrons and how they behave when we explode them. We'll talk about that when we get into spectroscopy. Super, super fun examples. It also predicts the atomic properties that are directly related to the behavior of the atoms. Why we have metals, why we have nonmetals, why when we exchange electrons in reactions, do some elements lose electrons and some elements gain electrons? Why are some elements just, practically inert, don't react, shoved up against the wall, don't participate in the party? And then some other periodic patterns. We will dive into a lot of these in Chapter 3, next unit. All right, so just to wrap up our idea of a wave, this is what we're going to really dive into in Chapter 2, the nature of light. We are going to focus our attention on the electromagnetic spectrum. Now, electromagnetic radiation is oscillating electric and magnetic fields. Electromagnetic radiation can be described as a wave comprised of these two different fields that are perpendicular to each other. So what we see is that that blue one is horizontal, flowing around there, and the red one is perpendicular to it on the vertical, up and down instead of left and right. And they both travel in a specific direction. Specifically for this diagram, that direction to the right. When we look at a wave, we can describe a few things. And those things that we can describe, first off, was amplitude and wavelength. Wavelength and amplitude are independent properties. Now, wavelength is from the distance from one peak to another. It's often abbreviated with the Greek symbol lambda. And it's often in units of meters or nanometers. Meters is the SI unit for length, but again, nanometers is a little bit more helpful for us in terms of our chemistry subatomic realm. Now, it's the actual distance between two peaks, or you can think about one oscillation, right? So what we see is this red one has a long wavelength. This one has a medium wavelength, and this one is a little bit smaller, this blue one, small wavelength. So we can call them long or large. We can call them small or short. all of those, because their distance descriptions are all very accurate. Now, amplitude or intensity is only the brightness. We will deal with wavelength more often because it's an intensive physical property, not dependent on the sample size. Amplitude is extensive, so it does depend on the actual sample size. Dim versus bright. And amplitude is going to be the distance from essentially point zero to a peak. We'll call it midpoint to peak. We don't do a lot with amplitude. We'll see a little bit when we discuss the photoelectric effect, one of Einstein and Planck's #1 experiments during the quantum mechanical development. But again, we'll see that it's not super, super important. Now, wavelength is not the only way to be able to describe something of a wave. Frequency also is. Frequency is annotated as this scripty V, nu, if you will, for the Greek symbol. It is the number of cycles or oscillations per given period of time. Most often, seconds. So if I want to just bring back another one of our waves here, let's just draw a wave. There we go. I can look at wavelength right here. There's lambda. It's not until I bring about, let's change it to green, the actual time that I can express a frequency. 1 wavelength, 2 wavelengths. So when we think about that per 1 second, that can be determined into a frequency. So frequency would be 2 per second, or seconds to the -1. You can write that a couple of different ways. 2 with a 1 over seconds. You can say 2 over seconds. Another unit is a hertz. 2 Hz. The hertz means literally per second, not the car rental place. Now, how we bring these guys together, these two extensive properties, is by looking at C, the speed of light. The speed of light is equal to 3.0 times 10 to the 8 meters per second. And what that is actually equal to is wavelength times frequency. Wavelength in meters, frequency in per second. So we can utilize this to convert. The speed of light is able to convert between wavelength and frequency, which are both very important values for us as we continue on in understanding the electromagnetic spectrum. We will practice with converting with these once we get into class. Here is our beautiful electromagnetic spectrum. Again, you do not need to memorize this, but this is just something to look at before we get into any calculations. What we generally see is that when we look at the wavelength versus the frequency here, long wavelength, or large number, corresponds to a low frequency. That's how we get the speed of light to be a constant. As one goes up, the other one goes down in terms of wavelength or frequency. Same thing over here, high frequency, short or small wavelength. Now, when we look at the electromagnetic spectrum, we see a lot of things. Let's just start over in the low frequency range, right over here, low frequency or long wavelength. This is also low energy. We'll talk about how energy plays a part when we see radio and microwaves. These are things that we have in our everyday life. We also see cell phones right there. AM, FM radios you might not listen to anymore, but they're still out there. These are low energy, low frequency, so their waves would look like this, right? Large distance between those two peaks, small cycles, a small amount of cycles per second, kind of looks slow and lazy. These are the things that don't really harm us. Infrared is utilized a lot. You can think about that in terms of alarm systems, or even in some detections of cancers. Infrared is utilized in a lot of different things. They utilized it a lot in airports recently with the COVID-19 crisis. You could use infrared to do body temperature. We are all chemical reactions happening throughout our body, and so some reactions are faster than others. What's utilized most in the research is cancer metabolism is faster than normal human metabolism. So usually we see infrared is a very unreliable but work in progress way of quickly finding cancer cells. If cancer cells rapidly multiply and have a high metabolism, they usually expel more heat than our typical normal body. And so you can actually see some very fast ways of determining some cancers. Breast cancer is one of the first ones that's being utilized to study infrared detection of cancerous cells. Then we get into our visible light, very small section of the actual electromagnetic spectrum. This is what we can see. These are the colors that we have. And then past that, we get into ultraviolet, UV. That's usually when we say, oh, sunlight's bad, don't get it. UV is higher energy than what we see normally with our eyes, but UV is still important for some reactions, specifically the production of vitamin D. If you've ever heard, go out in the sun, get your vitamin D, it's not that the sun is just giving it to you, it's that the sun's UV rays is actually making the reaction on your skin produce your own vitamin D, which is really important. And then we have X-rays and gamma rays, which are high energy, high frequency, and short wavelength. Those types of high energy waves, just to be different, very, very short wavelength there, short distance in between those peaks, but a lot of cycles per second. And so that's what we're going to be able to discuss throughout this next chapter. We won't go into the diffraction or bending of waves. We're going to skip that and go straight to the particle nature of light when we talk about the photoelectric effect. Thank you so much for joining me, and I'll see you next time. Hello and welcome as we dive in further to quantum mechanics. With this lecture, we will talk about some experimentation throughout the development of quantum mechanics, and we specifically will start off with the photoelectric effect. We'll see some calculations today, so a calculator will always be helpful when we dive into these types of calculations on the video. We'll get more practice in class as well. Where we left off last class was looking at the electromagnetic spectrum and understanding how light behaves. And really what we're trying to do with that discussion is understand and push a little bit further into quantum mechanics how electrons can also behave with energy light waves, so to speak. So what we're going to see today is that interaction between electrons and light, and how the first few experimentations really developed the idea of quantum mechanics that we have today. Okay, for when we think about the photoelectric effect, what Einstein and Maxwell Planck were trying to develop here was looking at how the particle nature of light. Now, yes, we were thinking about the electron, but what they were trying to do is bridge the gap between the wave-particle duality. And so focusing on the particle nature of light, they were trying to express the idea that light energy must come in packets. The photoelectric effect is a famous experiment that Einstein observed that when light shines on a metal surface, electrons are produced from that surface. So he would take, in an evacuated chamber, a metal surface. And what happened was, as he shined light on that metal surface, And I like how it's kind of brought up here, expanded for you. The light impacts the atoms of that metal surface and then ejects an electron. So you would notice a little spark. And so he called those electrons being emitted from the metal surface photoelectrons. They were somehow interacting with the light energy produced from the light and absorbing that energy in order to eject. Now, what was developed from this are a couple of new statements. Classical theory, this was before further development, but the photoelectric effect, according to classical wave theory, attributed the electrons being emitted from the metal surface to the light energy being transferred to the electrons. In classic theory, if the wavelength of light is made shorter or the light wave's intensity is made brighter, the electron should eject. What this means is that what was predicted was that wavelength and amplitude of a wave should affect the number of electrons ejected. That was Einstein's theory. At this time, both wavelength and amplitude were being looked at. So not only could they make the wavelength shorter and therefore more impact, more energy, they also thought the intensity, making the light brighter, would result in more electrons being ejected. The energy of a wave is directly proportional to its amplitude and frequency. That's what classical theory expected. They said if a dim light was used, there should be a lag time. Maybe the light should be like providing enough energy over time and build up that energy in the electron, and then the electron would eventually be emitted. This is wrong. What actually happened in Einstein's explanation using quantum theory was that it doesn't matter what the amplitude did not change anything at all. What does change is the actual wavelength. There was a threshold frequency or a specific wavelength that was needed in order to actually get the electron to eject. He called this the threshold frequency. Remember we talked about the speed of light in a vacuum is how we can convert between wavelength and frequency. What Einstein decided as an explanation for what he was observing is the amplitude doesn't matter. Light being dim or being intense, being bright, doesn't have any effect on the actual energy of that light. A high frequency light from a dim source can cause an electron emission without any lag, as long as the threshold frequency, as long as that frequency or that specific wavelength was met, that's all you needed. Changing the amplitude didn't change where the electron ejected. That's what he called the threshold frequency. Right there, using a high intensity light or low intensity light, the threshold frequency was the exact same. There wasn't a lag time. It occurred right at the same amount of time. The only thing that was different was a brighter light caused the electron to have a higher kinetic energy when it was ejected. That doesn't mean anything in terms of time. It doesn't mean anything in terms of the actual energy attributed to the light or the energy attributed to the threshold to get that electron to eject. What was developed out of this was a very, very important calculation, the energy of a wave. It's calculated one of two ways. Energy is equal to h, which is Planck's constant. Planck and Einstein did all of the mathematical work to develop what the threshold frequency was, times the speed of light, c over lambda, or energy is equal to h times the frequency. Now, h is Planck's constant. This will always be given to you. You do not need to memorize it. Sooner or later, we'll do enough calculations that maybe that number will get ingrained into your memory. But again, it will always be given to you in a question and on the front of an exam. 6.626 times 10 to the negative 34 joules times seconds. This is essentially, it's a constant to be a conversion factor between energy units, the joule, and the threshold frequency, the per second for a frequency. Now we can use, again, this calculation up here in order to, instead of using a threshold frequency, we can kind of use a threshold wavelength. All of those will be utilized in this calculation. Either one is fine. Now here's an example of what work they did and how they determined all of this energy business with wavelength and frequency and throwing out amplitude. A nitrogen gas laser pulse with a wavelength of 337 nanometers contains 3.83 millijoules of energy. How many photons does it contain? Well, the first thing that we would want to do is really address that wavelength and say, okay, if that's the wavelength of the laser, let's go ahead and find the energy. Find the energy of that actual wavelength. That will be the energy per photon. The energy per packet of light, so to speak. Remember, we're looking at the particulate nature of light. Now, this energy right here given, this is what we want to deal with second. This is the total energy of the pulse, right? In a nitrogen laser, we pulse with the light, but again, there's multiple packets, right? There's multiple photons within that pulse. And so these two bits of information will be able to figure out how many photons does the actual laser contain. But first, what we need to do is actually use the photoelectric effect calculation. Energy is equal to hc over lambda to find the actual energy of that one photon. So when we plug that guy in, again, Planck's constant is always going to be given to you. The speed of light will always be given to you. The only thing you would need to do is be able to look at those units and determine what units do I need for lambda, for my wavelength. So when we look at H and C, H is in joules times seconds, C is in meters per second, so therefore we see the seconds match up. We know that this has to be in meters. Why? In order to perfectly cancel with that of C. So taking my 337 nanometers, I would need to multiply it by 10 to the negative 9, which is my conversion factor between meters and nanometers. And then I could go ahead and do my overall calculation. So be very careful with that. Converting for unit sake, first setting ourselves up for success to make sure that everything cancels. When we look at this, nanometers cancels with nanometers. That's where we can get our meters canceled with meters, our seconds with our seconds. We are left with joules, which makes sense because we are in an energy calculation. So once we do all of this, we should be getting 5.90 times 10 to the negative 19 joules. Again, a measurement is nothing without the number and the unit. So please be aware of how we can derive those units and see with the given information what our final unit would be, joules. 3 sig figs. How I chose 3 sig figs is because of the measured value having 3 sig figs, so 3 sig figs in my answer. Now, this is the joules per photon. What the question is actually asking for is how many photons does the actual laser pulse contain? That's where we want to take our second step and say, well, if we know the amount of energy total, we can take that energy and divide it by the energy per photon. Use this new energy, the 5.9 times 10 to the negative 19 joules per photon, as a conversion factor. First thing we'll do is I'll start with that 3.8 millijoules and convert it into joules. There are 1,000 millijoules in 1 joule. Next thing I'll do is I'll take that energy I just calculated and say in 1 photon, there is 5.90 times 10 to the negative 19 joules. And that will set myself up. Now again, units cancel, millijoules with millijoules, joules with joules. I'm left with photons, which is what my desired answer should be. How many photons are there? We should get essentially what would look like a bigger number, 6.49 times 10 to the positive 15 photons. So why is this important? Well, when we're looking at a laser macroscopic world, we can see there is a lot of photons, subatomic particles encased in that. And this is really what was overarching the idea of the photoelectric effect. Now, at this point, what was really interesting about the photoelectric effect was, again, we started to talk about this a little bit last time. Energy was light, and matter was the electrons, protons, and neutrons. And there was a real division between energy and matter. Classical physics said before this, there is no intermediate between these two states. They are two separate identities. And so with this photoelectric effect and the development of quantum mechanics, there was a breakdown between that division of energy versus matter. And so now we can start to see how photons and light can intersperse together. What that did for us is it introduced the idea that light is quantized. Light has a particle nature, and so therefore electrons have a wave-particle duality just like light. The ejection of the electrons from the metal surface by the light was proof for Einstein that there was some sort of a binding energy. An electron wants to stay with the atom, but it has a price. For the right price, that electron will leave just the right amount of energy for it to escape from the atom itself. So when it's irradiated with a shorter wavelength photon, the electron absorbs more energy than necessary. Remember, a shorter wavelength means a larger frequency, which correlates to a higher energy. So even if you decide, hey, I'm going to promote that metal surface with higher energy than what's needed, that's great. The electron will still absorb that energy and it will be released. It's just getting more than what it needs. It will have a higher kinetic energy when it leaves. But that light is a packet of energy, and that was a huge thing in the early 1900s. We won't be doing any calculations with binding energy, only calculations of the energy of photons and the number of photons in a laser pulse. Now, again, early 1900s, 1910, 1920, this was around the same, the time of the birth of forensic science. I am a big history nerd, if you haven't determined that already, mainly just history when it comes to science and the development of things. But forensic science was one of my passions back when CSI first came out. That was right where I wanted to be. And so I learned a lot about the development of forensic medicine in the early 1900s. Now, think 1910, 1920. Back in those days, it wasn't very easy for investigators and police departments to determine what the heck happened to people when they ended up dead, right? With no evidence of a stab wound or a hanging or anything like that. Really, there was a loss for when people showed up dead, and coroners weren't really medical professionals. They were actually elected positions, so they were political positions. The actual medical examiner didn't start until the 1920s. And the reason why there was a demand for a scientist in the police department was because people were being killed with poisons. Now, emission spectra of elements are like a fingerprint. Each element has their own unique spectrum, and scientists started to do these experiments in the early 1910s, and those experiments really led the way for forensic science. One of my favorite books is called The Poisoner's Handbook. I'll share it with you in class later. There was a really good Nova episode too, if you're in that realm of watching Nova episodes. But The Poisoner's Handbook is a book that describes the process and the development of forensic science based off of really murderers trying to be one step ahead of the scientists and the one step ahead of the police department. This development of the emission spectra is really one of the births of determining how people were poisoned back in the day. Now, what scientists would do is take a pure element, usually in a gas. It could be other forms, but usually in a gas. So it's in a tube right there, and they would put a charge through it, supply some energy, right? Energy, light, call it light energy. What that would do is it would actually, it wouldn't emit electrons, but what they noticed was that light was then emitted from the actual sample. So they didn't provide enough energy for the threshold frequency to be met, but they provided maybe a little bit less energy to see what would happen to the sample. Now, what happened to the sample is that the energy would be passed through a slit and then through a prism, and it would split into the different visible sections. And on photographic paper, right, photographic film, you could read the lines. They were visible. And these corresponded to lines in the electromagnetic spectrum of the different color scales. So when we think about atomic spectroscopy, what atomic spectroscopy is really doing is it's playing with the idea that an electron is at a specific ground state. There's a specific point, particle nature of that electron in the electron cloud. Somewhere in the atom, there's an electron just chilling and sitting there. If you supply that electron with some energy, we'll call it HV to say it's light energy, right? That electron can get excited to what we call an excited state. That electron absorbed the energy and therefore jumped to a higher energy state. Now, it didn't leave. We're not doing the photoelectric effect. It just absorbed some energy and it moved. It's kind of like in the morning, I love my coffee. In order for me to get out of bed, I have to know that there's coffee waiting for me in the kitchen. So once I get my coffee, once I get that energy, then I can actually function and I'm excited and I can move around and do all sorts of different things. But eventually, just like everyone else, I will drop back down to the ground state. When I do, I have released some energy out into the universe, right? So I can absorb energy. There's the blue. And jump up to the excited state. Eventually, though, I will emit energy and relax back down to the ground state. Now, this is atomic emission spectroscopy. We can be able to determine where electrons are in the electron cloud by studying the amount of energy released. This is a very, very powerful tool. What forensic scientists used back in the day was since a lot of the early poisons in the 1920s and around 1922, 1923, roaring 20s weren't all jazz. Barium, arsenic, a lot of elemental poisons were brand new to criminals. And so what they would do was slowly feed people these barium-laced foods or arsenic-laced drinks, small enough quantities that the actual person may not understand or notice based off of taste that something was up, but just enough so that eventually they would die. Now, scientists noticed in forensic science, one of the births of this use of science to determine cause of death was they would take and clean out all of the bones of the people that died mysteriously, and they would lay them on photographic paper and shine light on them, and then develop that photographic paper, and the arsenic and barium were still in the bones. That's what happens when you poison people. The scientists will definitely catch up to you. So one of the original births of forensic science was developing photographic film with atomic emission spectra of people's bones. Very, very interesting. Here are just some examples of the elemental line spectra. Like I said, every single element has a different emission spectra. White light right there in the middle, this is the whole visible section of the electromagnetic spectrum. Usually it's between 400 nanometers to 700 nanometers. That's usually the range that we are talking about, sometimes 680, but we'll just go 400 to 700. You wouldn't need to memorize any of those fields. All of our discussions will be in the visible, and I'll let you know when that is. But you can see the different types of fingerprints. Now, hydrogen is very simple. Hydrogen has 4 lines, what we saw back up here in this lovely picture. There are the 4 lines, 1, 2, 3, 4, that very, very faint purple one. As we get more complex with the element, we see more complex emission spectra. Neon has 10 electrons. My goodness, there's all sorts of different lines there. And so what scientists were able to do is develop how to calculate the quantized state of the electron. Now, Einstein and Planck's photoelectric effect identified that light was quantized. So the emission spectra takes that one step further and says, well, electrons must be quantized then too. They must have particle nature within the electron cloud. And so it's the buildup of the electron cloud that we want to be able to discuss for the rest of this chapter. Now, what was developed from this was the Rydberg equation. Rydberg was a Swedish mathematician, and he helped with the development of this equation to actually analyze the atomic spectra and calculate the transition from a ground state to an excited state. Now, this work led into what we will be discussing a little bit next, which is Niels Bohr's development of the Bohr model of the atom. At this point, we do know that in the atom, there is the nucleus, which has protons and neutrons. And what was developed because of the quantization of energy was the idea that electrons exist in orbits around that nucleus. We'll call these n equals 1, n equals 2, n equals 3. And wherever an electron resides, it can shoot up to an excited state by absorbing energy, or it can relax back down and emit energy in any way, shape, or form. It can jump from any orbit based on whether it absorbs or emits energy. Now, the ground state will always be a lower energy orbital, a smaller number. Reasons for that, why is 1 the best, is because there's an attraction right here between the protons and the electrons. Opposites attract. And so when we think about the electron pulling away from the nucleus, jumping up from the n equals 1 to the n equals 3, that should require energy in our mind. That electron is trying to pull away from the center, which it's attracted to. Think about pulling a magnet off of a fridge. You have to physically go and pull it off. Now, when the electron drops back down to a lower energy orbit, that is where it releases energy, and that's the energy we see in the atomic spectra. So the Rydberg equation looks like this. 1 over lambda, the wavelength, 1 over the wavelength is equal to r, which is a constant, 1 times over 1 over n squared final, minus 1 over n squared initial. For this calculation to work, n final has to be less than n initial. N final should be a lower number, and initial needs to be a higher number. We are going to be calculating the wavelength emitted. So we are looking at the process of relaxing electrons. So let's just go ahead and practice a little bit. Let's imagine that we can calculate the lambda emitted when an electron relaxes from the n equals 4 to n equals 2 orbitals. Now, with this idea, what we want to be able to look at is plugging in. Again, n equals 4 is our initial, that's where it started. N equals 2 should be our final. If we start at 4 and end at 2, that is a relaxing process. Now R, again, will always be given to you 1.097 times 10 to the positive 7 inverse meters. Notice that we are calculating 1 over lambda. That's just how it was calculated. And so R is where we get that unit. 1.097 times 10 to the positive 7 inverse meters, 1 over meters. Let's go ahead and plug that in. 1 over lambda, 1.097 times 10 to the 7 meters to the minus 1. Just make sure that you're not forgetting those squared values. 4 minus 1 over 16. Again, 2 squared is 4, 4 squared is 16. Because of that subtraction right here, this is really why we need to make sure that our n values are going from high to low. Initial should be higher, final should be lower. If you switch it, it's not the biggest of deals, but what does happen is you'll get a negative wavelength, which should be a big red flag. That's a no-no. All right, let's go ahead and keep chugging along here. I'll just step out a couple of the calculations so you can follow along. We'll practice a lot more of these in class. Unitless number in that bracket. We don't have anything in terms of units for the orbitals. So this is one time when the n value there is just going to be a whole number. 1 over lambda is 2.06 times 10 to the 6 meters to the minus 1. And then we'll take the reciprocal of that. 1 divided by that answer. 4.86 times 10 to the negative 7 meters, or 486 nanometers. So we would see that's in the visible section. So that's one of the lines that we would see for this transition. Now, again, you wouldn't need to come up with all of those transitions. We'll see a nice little visual in a little bit with bringing in the Bohr model. All right, just be careful of the algebra on that one. Now, the Bohr model of the atom, we got the nuclear model of the atom with the Rutherford Gold experiment. It explained that the protons and neutrons were in the center. The electrons take up most of the empty space around the outside. But again, Rutherford did not explain any of the structure of the electron cloud. It was Bohr that developed a model of the atom to explain how the structure of the atom changes when it undergoes these energy transitions that were observed in the atomic emission spectra. Bohr's major idea was that the energy of the atom was quantized, and the amount of energy in the atom was related to the electron's position in the atom. And so the idea of orbits was starting to be developed, but not the idea of the energy of each orbit. And so that's what Bohr really brought to the table, was this idea that he was able to explain the atomic spectra and explain where the fixed orbitals were around the nucleus. It kind of looks like the nucleus is the sun and all of the electrons are planets rotating around it. And the transitions, either energy being absorbed or energy being emitted, were those lines in the emission spectra because of these fixed states. So electrons travel in orbits and they're fixed distance from the nucleus. Those are what he called stationary states. And so therefore the energy of the electron was proportional to the distance of the orbit. When we think about being close to the nucleus, again, we kind of already mentioned this, electrons attract protons. So the closer the electrons are to the nucleus, the more stable they are. They are happy to be there because they feel that attraction. As we emit or as we see the electrons absorb energy, they can jump up to higher orbitals. It's when electrons emit radiation, they should be jumping down from high energy to low energy. That emission spectra should be making the electron relax back down to a lower energy state. The distance between the orbitals was determined by the energy of the photon. So Bohr took this a little bit further and actually was able to say, what is the energy difference? Not only taking the wavelength emitted, he then went back and calculated the energy using the calculation that we had in the photoelectric effect, right? So we can see a couple of different cases here. All valid transitions and understanding the emission spectra that was visualized for different elements. Now, there's our little nucleus right there with the protons, that red dot. N equals 1 is the closest orbital to the actual nucleus. N equals 2 is a little further away, N equals 3, N equals 4, and it can go up as far as we can imagine. As we start to dive into chapter 3 and looking at the periodic table and elements and where these fit into specific elements, it will really start to be eye-opening of the expansive nature of quantum mechanics. Lovely. Another player in this time was Louis du Bois. And du Bois was around in 1924. He really wanted to emphasize the wave nature of matter. The particle nature was very well understood at this point with the Bohr model of the atom. And the transitions were understood as particle nature, even though they had some sort of wave nature with that emission. The actual movement of the electron between orbits was very, very much focused on the particulate side of the electron. And so Louis du Bois really came in order to say, hey, what about the wave nature? We're missing that part of quantum mechanics. And so he looked at electron diffraction, which electrons diffract just like waves do. And so they must travel in that wave style up and down motion, right? Even though we're not talking about light, we're now talking about the electron. If light can behave like a particulate, then why can't electrons behave like a wave? And so duality, just like the cat, right? Just like the thought experiment from Schrodinger, du Bois came up with his wavelength. And the du Bois wavelength, usually abbreviated lambda with a dB, is related to the kinetic energy of the actual particle. Specifically, we're going to talk about the electron. Now, this du Bois wavelength, this wave nature of matter, is the wave nature of all matter. It doesn't matter how big or small. Everything that has matter has wave-particle duality. Now, we will be able to discuss why we don't see a car moving in this same pattern of up and down, and why we see an electron react that way or move that way. But again, everything that has kinetic energy has that motion of wave particle duality. And so this is his wavelength equation. H, Planck's constant, divided by mass times velocity. So let's just define a couple things. This is Planck's constant that we had seen before, again, always given to you. 6.626 times 10 to the negative 34 joules times seconds. This is mass. Now for mass, we have to be in kilograms here. The reason is because of the joule. 1 joule is defined as 1 kilogram meters squared over seconds squared. And so mass, in order to be able to calculate correctly and cancel out with the joule, we have to have mass in kilograms. V is velocity, the movement in meters per second. So when we look at this calculation, we can calculate the wave nature of any moving particle, whether it's a subatomic particle or a macroscopic particle. We'll do the electron right now, and we'll do more things in class to be able to say, wait, why doesn't a car move up and down like a wave? Why can't we see that? Why when we think in a straight line? The reason that du Bois was so emphatic about making sure that the wave nature was understood for the electron is because in the macroscopic world, we don't often see the wave nature. We can calculate the du Bois wavelength for a macroscopic particle like a car, but what we'll see is it's very, very small. And so therefore it's negligible. But for the electron, it's not. For the electron, because its mass is so small and its velocity is so large, we really see a tipping point here in this calculation and why it's so important. So find the wavelength of an electron whose mass, if we remember from way back in chapter 1, 9.11 times 10 to the negative 31 kilograms. If it travels, it's a good indication that it's the de Broglie wavelength, the traveling part, at 2.65 times 10 to the 6 meters per second. Again, that's just plugging in to this calculation. 6.626 times 10 to the negative 34. I'm going to write out the full kilograms meters squared over second squared so that we can see what we're left with. And then we get to put in the kilograms here. 9.11 times 10 to the negative 31 kilograms times velocity 2.65 times 10 to the 6 meters per second. Lovely. So when we go ahead and plug that in and do the math, we should be getting 2.74 times 10 to the negative 10 meters. We can see that that is a small number, but when we compare it to the size of an electron, it's not that small. And when we see that, it actually ends up not quite in the visible spectrum, but close to the visible spectrum. Here is the principal levels in the hydrogen atom. This is what the Bohr model really started to get into with looking at all the different types of transition states that an electron could take, noticing that the electron could start down here at the n equals 1 and shoot up to essentially infinity, but really could drop down from 5 to 1, 4 to 1, 3 to 1, 2 to 1. It could go from 5 to 2, it could go to 4 to 2, it could go from 3 to 2. There's a lot of different transitions, which is why when we get more and more electrons, our atomic emission spectra get more complicated. Now, most of you have probably heard about Heisenberg's uncertainty principle, or at least the name Heisenberg. With Heisenberg, he stated that the product of the uncertainties in both position and speed of a particle was inversely proportional to its mass. What this actually means is that the position, the particle nature, the velocity, the wave nature of an electron cannot both be known at the same time. The more accurately you know about the position of a particle, the less you know about its speed. And vice versa. The more you know about the speed of the electron, the less you know about the position. This was the problem with studying electrons and protons. All of these subatomic particles have wave-particle duality. And what that means is they're very complex. The more you know about one aspect of that subatomic particle, the less you know about everything else about it. So we as scientists must look at the type of experiment that we are performing and really say, what am I trying to study? The position, the particle nature, or the velocity, the wave nature? I can't know both. There's that really funny joke about Heisenberg driving through Munich in his car, and he gets pulled over by a police officer, and the police officer says, "Do you know how fast you were going back there?" And Heisenberg just looks at him and says, "No, but I know where I was." Wave-particle duality and the Heisenberg uncertainty principle. Lovely. Now, what does this tell us for quantum mechanics? Well, because we can't know both the position and the velocity of an electron, we can't really predict a path that it will follow. We don't know exactly where an electron is, but we can do a probability distribution. We can do some math. The Schrodinger equation tells us that we can actually determine a good probability of where the electron is, but we can't do a classical trajectory like in normal physics in the macroscopic world because of our wave-particle duality and the wave nature being really important for our electron. We only can at best say where the probability of an electron is. We won't get into the Schrodinger equation. It has to do with H, the Hamiltonian operator, and wave functions. There's a lot going on in these, but what is really important for us is that Schrodinger did the math. If you take physical chemistry, which is usually in your junior or senior year, if you're a chem or biochem major, excellent class, really exciting. However, the only thing we need to know is that when we plot a distance versus psi squared, it represents an orbital, a probability of where the electron will likely to be found. We'll dive into these a little bit more once we discuss the actual locations of where an electron could be. I say could because it's a probability. Quantum numbers. Quantum numbers are our solutions to the wave function. Now with quantum numbers, there are 4 main quantum numbers. We're going to go over all of them individually and see how they are related to each other. But here are the main 4. The principal quantum number, the utmost important one, that is n. That's the n that we were talking about before. It's an energy level. N is going to help us determine what orbital level we're at. N equals 1, n equals 2. We'll talk about that in just a second. The angular momentum quantum number is L. That tells us the orbital type. What's its shape? What does it look like? What's the probability distributional map look like when we plot out psi squared? The next one is the magnetic quantum number. M sub L is how it's spoken. ML if you really want to forget the sub part, but it is a subscript for that little L. And that tells you the position of the orbital on an XYZ plane. So if we think about the orbital type L, and we put it now in a 3D Cartesian plane, how can we see the orientation take shape? And then the spin quantum number, MS, that's the orientation of the actual spin. This describes not technically what the orbital looks like, but the traveling of the actual electron. So let's just get into a couple of these more specifically. We'll start with the principal quantum number. I'll abbreviate quantum number QN. And the principal quantum number is that lowercase n. Again, this describes the size, the energy, of the orbital. Now, when we were talking before and we said, here's the nucleus, there's n equals 1, n equals 2, n equals 3. Those are the same principal quantum number that we are discussing. Now, the larger the n starts at 1, 2, 3, all the way up to infinity. The larger the n, the further away it is from the nucleus. So what that means for us is that the energy will be greater. When we think about increasing energy, as you move away, from the nucleus. This can be calculated. The energy at a specific energy level is equal to the negative 2.18 times 10 to the negative 18 joules times 1 over n squared. Now, that energy is negative because it's the electron, and it's the interaction, the attraction between the electron and its nucleus. Opposites attract, so that energy is negative, but that negative number will get smaller and smaller and smaller, closer to 0 as we move away. What we also see with this is that because it's n squared, as n increases, the energy difference between orbitals gets smaller. So the spacing between n equals 1 and n equals 2 is the biggest difference in energy, or the biggest distance. As we get further and further away, if we were to plug in n equals 5 and n equals 6, that difference in energy is very, very small. We'll get into that a little bit more when we start to do our chapter 3 information with how does this relate to the actual electron itself in a specific element. All right, so n equals 1, 2, 3, 4. That's all you would really need to know right now. It's how it relates to the angular momentum quantum number that's important. Angular momentum quantum number. Again, L, it's a little scripty L. L is equal to 0, 1, 2, all the way up to n minus 1. Now, this is a range of possibilities. All we want to be able to say with these quantum numbers is, does this position exist? Can we look at N, L, and ML and see a physical orbital in our electron cloud? So if N equals 1, the only possibility I have for L is 0. If N equals 2, L could be 0 or L could be 1. It's the range always from 0 up to n minus 1. If n equals 2, L could equal 0, L could equal 1. Oh, excuse me, 3. I did 2. If n equals 3, L could be 0, 1, or 2. And the last one that we'll stop at, if n equals 4, L could be 0, L could be 1, L could be 2, or L could be 3. There are an infinite amount of possibilities with n, which means as we increase n, our options for L also increase. Now, quantum numbers are a very tricky subject. However, we do have a way of describing each one individually, but seeing how it's based off of the previous. Now, looking again at the zeros and the ones and stuff, that's difficult. So what we decided as chemists is to give this angular momentum quantum number a more definitive letter denotion. Because this quantum number is going to describe a shape of an orbital, we give the actual numeric value a letter. 0 is the s orbital. It's a sphere. I'm going to try to nice little shading on that sphere. Again, thankful that my parents told me, don't be an artist, go be a chemist instead. No, I still like to do art, but it's nice to have that be a hobby and not a job. Again, no matter what the n is, if L is 0, that's the s orbital, which is still a sphere. The only difference between the n equals 1 s orbital and the n equals 2 s orbital is the size. Larger s versus a smaller s. We know large versus small because of the n value, the shape, the sphere, because of the L value. If L is 1, that's what we call a p orbital. A p orbital looks kind of like a figure 8. We'll do some shading on one side, usually a shaded side and an unshaded lobe there. So again, L equals 0, that's S. L equals 1, that's P. If L equals 2, that's the d orbital. These look like a clover. It's kind of like 2 p orbitals are kind of hugging. Again, shading on some of those lobes. L equals 0 is S. L equals 1 is P. L equals 2 is D. L equals 3 is the F orbital. I'll show you what the F orbitals look like, but again, the ones that I really want you to be able to recognize the shape for is the sphere and that figure 8 or the dumbbell shape for S and P. Lovely. Too far. Going to our third quantum number, the magnetic quantum number. That's the M sub L. This is going to describe our orientation on a 3D Cartesian plane. So it is described as the range of minus L to L plus L, including 0. Simplest one, if n equals 1, L equals 0, ML equals 0. What that means is if I think of a 3D plane, X, Y, and Z, if I put a sphere there, right in the middle, there's no way that I could rotate that sphere to make it look different. Think about rotating a ball. It's symmetrical, right? So there's only one orientation for that 1s orbital. Excellent. When n equals 2 and L equals 0, ML also equals 0. The 2s orbital has one orientation. No amount of rotating that ball will make it look different. Now here's where we get difference. When n equals 2 and L equals 1, the 2p orbital, if we plug in our options for ML, it's the range from minus L to plus L, including 0. That is 3 orientations. The minus 1, the 0, and the plus 1. 3 values there, so 3 orientations. What that means for us is if we imagine the p orbitals on an XYZ plane, I can actually imagine one of the p orbitals being along the x-axis. So it might get a little bit fuzzy. I'll zoom in. One of them being along the y-axis, and one of them being along the z-axis. Doesn't matter where your shading goes, it just makes it nice and pretty. This would be what we call the PZ. This is our PY, and there is our PX. The 3 orientations. Notice how, because of that P shape, that dumbbell looking shape, the figure 8 shape, we can imagine it rotating on the XYZ axis and looking different. Just to do a couple more. If n equals 3 and L equals 0, ML again equals 0. So the 3s orbital, again, it's a sphere, so the shape is dictating the orientation. N equals 3, L equals 1. The p orbital has an x, a y, and a z orientation. If n equals 3 and L equals 2, the d orbitals a -2, a -1, a 0, a +1, and a +2. 5 orientations. Yikes. And then let's just imagine our last option. If n equals 4, let's just jump to L equals 2 for the, or L equals 3 for the f orbitals there. The f orbitals, -3 all the way to +3, including 0, 7 orientations. Lovely. We'll be able to look at those images in just a second. I want to show you the positions in the sphere and the dumbbell and what the Ds look like, and the theoretical positions or shapes of the f orbitals. Again, all of these are mathematical probabilities. So we can't see them with a microscope, but they are mathematically driven. The last quantum number doesn't really describe the atomic orbital, just describes the actual magnetic spin. Quantum number, m sub s. M sub s means that the actual electron could be a -1/2 spin or a +1/2 spin. We'll get into this one a little bit more in section 3 of chapter 3. Right now, all you would need to be able to know for this is the actual values. MS can either be -1/2 or +1/2. It is unrelated to any other quantum number. So just like how L was determined by N and ML was determined by L, MS is independent of all of those other ones. It's just the fourth quantum number we need once we start building up our electron clouds with specific elements. Okay. Now, why we have these shapes and how the actual math works, I'm going to just briefly identify and show you some pictures. When psi squared is determined, it's the probability density. And it's the probability of finding an electron at a specific point in space around the nucleus in the electron cloud. Now, most likely area to find the atom's electron as you decreases as you move away from the nucleus. Now, nodes are probabilities of 0. It's when the function says that there is not any likelihood that the electron is there. One very big node is the actual center where the nucleus is, that the electron cannot be in the nucleus. That's not what we have determined for our electron atomic orbital. But we'll see in other shapes as we move away, there are more nodes. For instance, here's the probability density function for the s orbital. Notice how there's a whole bunch of dots. It's a whole bunch of just dots scattered around, and then it has some sort of radius right here when it gets to the lack of density around the outside. The height of curve proportional to the probability density is psi squared, and the density of dots proportional to the probability density tells us the shape. Notice how when we do the math, this does look like a sphere along our x, y, and z plane. Now, we don't need to do all of this, but this was where the total, or the distance from the nucleus was plotted based off of total radial probability. This is how we know the size of the actual s orbital, or the 1s orbital, 52.9 picometers. So again, these are all calculated based off of hydrogen. Hydrogen is the most easy to calculate using the Schrodinger equation. because it has only one electron. Once you get up to more than one electron, things get a little bit crazy, and you can't do it by hand anymore. You have to use a supercomputer, and so that's what everything's been determined after that. But everything is based off of the hydrogen nucleus. So I know some of you might be like, well, Harry, if it's just off of hydrogen, like that's not real science. This is the best we got, all right? So you can do the math for us if you want to, but all of these are just looking at them and saying, oh, look at that beautiful picture. What this tells you is that when you get into the 2s and 3s, as your n equals 2 and L equals 0, or n equals 3 and L equals 0, the only thing that changes is the size. But what also comes about are more nodes. Now, what are these nodes? There's a big node right here, and that happens to be the 1s orbital. And for n equals 3, there are two nodes, the 1s orbital and the 2s orbital, which tells us one thing. These actual positions are unique, and you can't get any overlap with bigger orbitals. That's really important to know. When L equals 0, we have the s orbital, right? The number of nodes is going to be determined by n minus 1, so that's how we can calculate that. For the n equals 1, there is essentially no nodes except for the actual nucleus, right? The electron can't be there. But once we get bigger and bigger and bigger, n equals 2, 3, 4, the number of nodes does increase, but the shape is still spherical. Here are the P's, the illustration of the 3 types of P's on the X, the Y, and the Z. There's your X axis, your Y axis, and your Z axis. You don't need to know any of the radial distribution functions. It's just the shape itself in that probability scatter chart. Ooh, 5 types of d orbitals. We know that there are 5 types of d orbitals because there are 5 MLs, right? When we have d orbitals, that's L equals 2. And so ML is minus 2, minus 1, 0, plus 1, and plus 2. Lovely. Here they are. Aren't they pretty? You do not need to know these at all. You do need to know that there are, when L equals 2, that's a d orbital, and that there are 5 orientations for those d orbitals, but they're highly complex, so you would not need to draw these ones. F orbitals. These exist only in very specific circumstances. If you are an inorganic chemist, which I am not, you spend a lot of time in the F orbitals. We'll see where they are in terms of on the periodic table, what elements have these. They're rather large elements. The lanthanides and actinide series is known for being, their outermost electrons are in the F orbitals. So those are the reactivities and people who do those. I had a very good friend in grad school who is now a professor at USC, who deals with lanthanide catalysts. And so she deals with a lot of the F orbital experimentation type things. The phase of an orbital, why I shaded some things and didn't shade the other, comes with identifying the actual phase of the orbital, and those are mathematical wave functions. You do not need to know that. That would be way, way advanced organic chemistry. All right, so thank you very much. This concludes our discussion of Chapter 2. We'll practice quantum numbers and being able to determine the relationships between N, L, NL, and then NS as we move forward. We will continue with these quantum numbers in Chapter 3, so make sure that they are not something that you just drop off and say, oh, they'll disappear. They will never disappear, ever, ever, ever. So please make sure that you learn to love them now. Thank you very much. I'll see you in class.